Diels-Alder reaction. Diels-Alder reaction is a very useful reaction as it creates two new carbon-carbon single bonds and also forms a cyclic compound. The reaction was discovered by Otto Diels and Kurt Alder, and they shared a Nobel Prize in 1950 for this exemplary work. Here is the reaction. A diene and a dienophile react in the presence of heat to form a cyclic compound. And this cyclic compound will have the framework of cyclohexene or substituted cyclohexene. A diene is basically a compound that has two double bonds. For Diels-Alder reaction, we want this diene to be a conjugated diene, where you can see that there's alternate double and single bonds. And the dienophile is basically a lover of the diene. The Diels-Alder reaction is a pericyclic reaction in which there is cyclic shift of electrons. This is going to result in a cyclic transition state which will be finally producing the cyclic compound. And because of this, the Diels-Alder reaction can also be called as a cycloaddition reaction. Like other reactions, the Diels-Alder reaction can also be considered as a reaction between nucleophile and an electrophile. Here, the diene is going to act as a nucleophile and the dienophile is going to act as an electrophile. First, to begin with, the electrons from one of the pi bonds is going to make a nucleophilic attack on the electrophilic carbon of the dienophile. This is going to create as a new carbon-carbon single bond. So here will be the new carbon-carbon single bond, and this is going to thrust the electrons from the pi bond of the dienophile to make an attack on this carbon, and this is going to create another single bond. So here are the two new single bonds that will be created. And these electrons right here will shift towards this carbon-carbon single bond to form another pi bond. Now all of this is going to take place at the same time, and therefore this reaction, this mechanism here is a concerted mechanism. Let's draw the cyclic transition state that will be obtained. Here is the cyclic transition state, and from here it will form as a product which is the substituted cyclohexene. Now in the product we could see that there are two new sigma bonds that are created and there is one new pi bond that is created. So these two are sigma bonds and this one right here is a pi bond. Diels-Alder reaction is an example for 4+2 cycloaddition because you can see there are 4 electrons from the diene and 2 electrons from the dienophile participating in the cyclic transition state. The substituents present on the diene and the dienophile will have a greater impact on the Diels-Alder reaction. Say for example, whenever you have an electron withdrawing substituent present on the dienophile, this is going to increase the reactivity of the dienophile. Let's take an example. Here we have a dienophile and you can see that there is an electron withdrawing group. The cardinal groups and the cyno groups are some examples for electron withdrawing groups. Let's draw the resonance contributor for this dienophile. So for which these electrons are going to shift here in the pi bond. The electrons from the pi bond is going to shift onto oxygen. And here is the resonance contributor. Now you can see from this from the resonance contributor that there is a partial positive charge that's going to exist on this carbon, right? Now because of which these electrons from the diene can make a nucleophilic attack on this electrophilic carbon. Now if you do not have this electron withdrawing group, then we will not be creating any partial positive charge on the molecule. So therefore the electron withdrawing groups on the dienophile is going to increase the reactivity of the dienophile and therefore make the Diels-Alder reaction easier. And in the same way, any electron donating groups present on the diene is going to increase the reactivity of the diene. Now let's do this with an example. So here we are going to put an electron donating group. So these electrons that is present on the oxygen is going to be shifted in here. That's going to result in a negative charge on this carbon. Let's draw the resonance contributor to see this. Now you can see that there is a negative charge on this carbon. Because it has got a negative charge on this carbon, it can easily go and attack the electrophilic carbon of the dienophile. Let's say if you do not have this electron donating group, this carbon may not have a bunch of electrons and therefore the Diels-Alder reaction may not be very effective. So having an electron donating group on the diene and having an electron withdrawing group on the dienophile is definitely going to make the Diels-Alder reaction easier. Here are some examples of Diels-Alder reaction. By varying the structure of the diene and the dienophile, you can get a wide variety of cyclic compounds. Okay. Now here we do have a strongly electron withdrawing group. This is maleic anhydride, which is a very powerful dienophile. Okay, because you do have two carbonyl groups, right? So this is going to be a very powerful dienophile. And for this reaction, you don't have to heat it to really high temperatures. The reaction only takes place at 20 degrees Celsius. But for other reactions, we have to heat it at a high temperature. This is the cyclic product that is obtained. And you can see again that this is the cyclohexene framework that will form the base for all the products. Okay. And the Diels-Alder reaction can also take place with dienophiles where there is a triple bond. So here is an example for it. Whenever that happens, you will be having an extra double bond in the cyclohexene molecule. Here is an example for a double Diels-Alder reaction. Here is a dienophile, and this dienophile is symmetric. Therefore, we can divide this into two equal halves. So let's do that. So here is one half, and this is the other half. And each of these halves is going to react with the diene separately to give us the final compound, which is a tricyclic compound. For the first Diels-Alder reaction, the diene is going to react with this part of the molecule. And here is the product. And here again, you can see that this is the cyclohexene framework. And the rest of the parts of the dienophile is just carried over. Once the first Diels-Alder reaction is over, this part, the second half, is going to react with another equivalent of the diene. Okay, and it's going to give us the final compound, which is a tricyclic compound. And here again, you can see that the cyclohexene framework is formed, right? And let's identify the sigma bonds that are created. So here are the new two sigma bonds, okay, and here is the new pi bond. And in the same way, these are the new two sigma bonds and the pi bond for the second Diels-Alder reaction.